Hello everyone, this is lecture 4 of course PE 500. In this lecture, we will deal with the second order linear differential equation. And the second order linear differential equation follows the general form of a of t as a function of t, the second derivative, another coefficient, the first derivative, another third coefficient, and y equal to g of t, where a, b, c of t may depend on the independent variable t or may become constant. G of t is a driving force function, and this term can become constant 0, a function of t. And if this term becomes 0, this will make this function as a homogeneous function. So we can call it a self-contained function without external inputs, and a non-homogeneous function where g of t doesn't equal 0. It can be a constant or can be a function of t. And in this case, the system is influenced by an external forcing function. And because that there is a second order derivative in the formula or the equation, there are different behaviors of the solution. So you can find an oscillatory solution. And in this case, you can find sine and cosine waves, or one of them, like what you are seeing here. You can say exponential or damped behavior. For example, there is a damped solution where there is an oscillation and then it decreases slightly until it reaches to be stable. It can be growth or decay solution, such as what you are seeing here. Then is an exponential growth over the time. So we need to understand each of them and how to determine that your equation or where your formula will give an oscillatory solution or damped solution or any type of different behaviors. So first, to do that, you need to understand the meaning of homogeneous and non-homogeneous equations. For a while, we mentioned that a homogeneous equation doesn't have a driving force or an external force, so the term g of t will equal 0. And here, we are focusing on the nature behavior, and the solution will be determined using the coefficients of the differential equation a, b, and c. And this is an example of a differential equation which is categorized as a homogeneous equation, because once you find a 0 on the right hand side, or you can get a right hand side with a 0, then you can determine that there is a homogeneous equation. But a non-homogeneous equation, you will find an external force on the right hand side, so g of t doesn't equal 0. And in this case, the non-homogeneous equation will capture how the system responds to external inputs. For example, g of t equals sine 2t, and in this case, it's called non-homogeneous. So simply, if the right-hand side can be 0 or 0, then it's homogeneous. Otherwise, it's non-homogeneous. Once you find the homogeneous differential equation and the coefficient a, b, and c are constants, then you can handle that using a characteristic equation. And based on that characteristic equation, you can find the different solutions with the different oscillation types. So to handle the characteristic equation ensures that your formula or your equation is homogeneous and a, b, and c are constant coefficients. In this case, let's assume that we have a solution on the form y of t equals exponential of rt, where r is a constant. And we assumed that solution because simply its derivative and integration are the same, and commonly it arises naturally when solving different linear differential equations that contains constant coefficients, and there are many mathematical and practical justifications behind that. So let's assume we have that solution. Based on that solution, substitute in the equation. So simply e exponential rt will, the derivative of the exponential rt will be re rt. So take this, substitute it here. The second derivative will be r squared, the exponential of rt, substitute it here, and y will be the exponential rt. Now we have a formula. Divide by exponential rt, and this because the exponential of rt will never become 0. There is a typo here, so this should be unequal. So the equation will become A multiplied by R squared plus PR plus C equals 0. And this simple algebraic equation is called the characteristic equation. And in this case, it's easier to be solved and find the different values for R. So simply, to solve a homogeneous differential equation with constant coefficients, simply write the differential equation in the standard form. Second, formulate the characteristic equation on this form as we derived it from a while. Using this characteristic equation, solve and find the roots using the quadratic formula, negative b plus minus the square root of b squared minus 4ac, all are divided by 2a, so that you can find R1 and R2. And if you remember in math, the quadratic formula has 3 cases, and we can determine that using the discriminant, which is under the square root, b squared minus 4ac. If the discriminant is greater than 0, then we have real and distinct roots. If it's equal 0, then we have real but repeated roots because they are equal. And if it's below 0, then we have complex roots. So we have 3 cases. Once you get the case, now you can write the general solution, and we have different solutions based on the case that you got based on the discriminant. So in case 1, which is real and distinct roots, the discriminant is above 0. Simply R1 and R2 are different. So in this case, the general solution will be C1 multiplied by the exponential of R1 multiplied by T plus C2 multiplied by the exponential of R2 multiplied by T. So based on the general solution, we can solve the different homogeneous differential equation with constant coefficient under case 1. And if you have initial conditions, we will find the value of C1 and C2. And in this case, you will get y of t. And it's our aim to get y of t so that we can plot the function and interpret it. Let's get an example. We have a differential equation, homogeneous, constant coefficient. So we can use the characteristic equation to solve it. How? Simply substitute in the characteristic equation. A is 1, B is negative 5, C is 6. Substitute. Based on that, get the discriminant, which is b squared minus 4ac. B squared is 25 minus 4ac. 1 multiplied by 6 is 24. So 25 minus 24 is 1 above 0. So we are in case 1. So we can get 2 real and distinct roots. If you substitute it in the quadratic formula, you will get R1 equals 2 and R2 equals 3. So in this case, we have the general solution to be C1 multiplied by the exponential of ET plus C2 multiplied by the exponential of 3t. For case 2, if the discriminant is equal to 0, then simply all of the roots are equal, R1 equals R2. And in this case, the general solution will be like that. C1 plus C2 multiplied by t, all are multiplied by the exponential of RT. Let's get this example. Ensure that it's homogeneous, constant coefficients. Categorize it simply by the discriminant. B squared is 16 minus 4ac. 4 multiplied by 4 multiplied by 1 is 16. So it's 0. So in this case, it's case 2. So we have repeated roots and both are reals. Substitute in the quadratic formula, we'll get R1 and R2 equals 2. Use that value, substitute to get the general formula. C1 plus C2 multiplied by t. All are multiplied by the exponential of 2t because R equals 2. The third case where the discriminant is below 0 or less than 0. Case 3, simply the general solution would be like that, and R will be complex alpha plus minus beta I, and in this case the general solution will be exponential of alpha t multiplied by C1 cosine beta t plus C2 sine beta t. Let's get this example. Homogeneous, constant coefficients. Then you can use the characteristic equation. Based on that, you can get the discriminant. B squared 16 minus 4ac. 4 multiplied by 13. For sure, z is larger than 16, so it's below 0. So it's complex roots. Substitute in the quadratic formula, you will get the roots minus 2 plus minus 3i. So alpha will be minus 2, beta will be 3. Use these two values, substitute to get the general formula, exponential of negative 2t, because alpha is negative 2, multiplied by c1 cosine 3t, because beta is 3, plus c2 sine 3t, because also beta is 3. Now, we understand that for each case, we have a specific general solution. And if you have initial conditions for this problem, then we can find the constants C1 and C2. By getting C1 and C2, you can get the full formula or the specific formula for y of t. By getting y of t, we can plot it and understand the behavior of the system. Now, we have 3 examples. We need to find the characteristic equation, then the discriminant, and then the root type, the roots, and the general solution. And remember, these are different steps to solve the characteristic equation for homogeneous differential equation. Ensure that all of them are homogeneous, 0, 0, 0, and contains constant coefficients, ones, constant, 10, 9, 5 are constants, so we can proceed with the step. For the first, convert it to the characteristic equation, you will get r squared minus 7r plus 10 equals 0. The discriminant b squared minus 4ac will equal 9. So we are in case 1. Substitute in the quadratic formula. You will get 5 and 2. So the general solution will be like that. For the second, get the characteristic equation. Get the discriminant. You will find it's 0. So you are in case 2. Substitute in the quadratic formula. You will get it to be 3. And based on that, you will get a general solution like that. The third example, substitute to get the characteristic equation. From it, find the discriminant, it's negative. So you are in case 3. You have complex roots. Substitute in the quadratic formula to get these roots. Then you will get the general solution that looks like that. Now, let's recap what happened. We have a second order differential equation with a right-hand side, g of t. If the right-hand side is 0, then it's a homogeneous equation. Otherwise, it's non-homogeneous. There is a special case. If it's homogeneous and it contains constant coefficients, a, b, and c, then we can use the characteristic equation to find the general solutions. And these general solutions can be used to plot the system. Inside the general solution, we have 3 different general solutions based on the discriminant. Case 1, different and real roots. Case 2, real and equal roots. Case 3, complex roots. And for each case, we have the corresponding general solution. Now, after understanding the meaning of homogeneous and non-homogeneous equations and how to declare the general solution for the homogeneous equation based on the discriminant, let's take another concept called oscillatory systems. And oscillatory systems are dynamic systems that exhibit repetitive behavior over time, often modeled by second-order differential equations. And these systems can be found in different fields such as biology, bioengineering, and physics. And the second-order linear differential equation for an oscillatory system can have the general form as you see here. The second differential equation multiplied by m plus the first differential equation multiplied by c plus x multiplied by k equals to the external force. And this equation models the mass spring damper problem, where the m is the mass here, c is a damping coefficient from the piston, and k is a spring constant from the spring here. And many applications in bioengineering, biology, and physics can be modeled using that simple model and this simple differential equation. By all means, we have the second derivative multiplied by m, or a constant, the first derivative multiplied by a constant, and the displacement or the variable multiplied by another constant. So m, c, and k are constants. The f is a function of t, and if the force is 0, then it's homogeneous equation, and if does not equal 0, then this is non-homogeneous equation. And the benefit of studying the oscillatory systems is that these systems can be found anywhere and in many applications, and we need to study whether the oscillation in that system will be damped or will not be damped after a certain while, and what type of oscillation and what is the corresponding solution or general solution that can be followed to plot or to visualize this system. So the first type of the oscillations or the oscillatory behavior is called undamped oscillations, and here you will find pure sinusoidal motion without energy loss, and this is a system that oscillates indefinitely without any loss of energy. And if this is the general solution of the oscillatory system, then the undamped oscillation will not contain the first derivative, and the mass is 1, and k equals to omega naught squared, and the external force will be 0, so that we will retrieve and get this final equation, the second derivative, plus omega naught squared multiplied by x equals 0. So omega naught here is a natural angular frequency of the oscillation, and x is a displacement or deviation from equilibrium. And if you are modeling a system and you found the final equation or the final differential equation of that system looks like that, then this system is under the category of the undamped oscillations. And in this case, we have a general solution, x of t equals a cosine omega naught t plus p sine omega naught t. And this equation is a pure sinusoidal waveform with a constant amplitude. And this equation can be found in multiple applications, such as idealized heart rate dynamics in the absence of fatigue or resistance. In other words, steady-state heartbeat under controlled conditions. And this should be the corresponding figure. The oscillation is repetitive without any damping. Damping here means that the amplitude isn't reduced over time. So if you notice here, it's between -1 to 1 over time. As you also notice here, -1, 1, and 1. So there is no sort of damping this oscillation over time. Now we need to know how to plot this figure or plot and undamped oscillations using Python and MATLAB. Go to the script named Lecture 4, Lab Exercise 1, Undamped, and the aim of this script and the corresponding MATLAB script is to define the function and plot it so that we can understand the curve of the undamped oscillation. First, we imported the necessary libraries, NumPy for mathematical operations and Matplotlib for plotting. We defined omega naught and amplitude, which is A, as we have here A and B. A is a constant, B also is a constant, and B got two different values, and both of them are plotted to check the difference. And it's noted that B is the phase shift. So if B is equal to 0, then there is no phase shift. And if it's 1, there is a phase shift with a value of 1. Omega naught is 2 pi, A is 1. We defined the time space by 1000 points between 0 and 5. You can increase the time if you need to plot it with more time. Then we define the equation A cosine omega t plus B sine omega t for P equals 0 and P equal 1. So now we have x1 and x2. We can plot both of them now using Matplotlib. We created a figure. We plotted both of them, the first in blue and the second in orange. We put a title, labels, grid, legend, and applied title layout. Finally, we saved the figure and displayed the same for MATLAB code. We defined omega naught 2 pi, A equals 1. We defined the time space or the horizontal line from 0 to 5 with 1000 points. In case 1, we defined B equals 0 and got x1. Then we defined case 2, B equals 1, which is the phase shift, and got x2. Then we plotted the first plot in blue and the second plot in red. We set a title, labels, legend, and as we mentioned, we set here hold on because you are plotting multiple plots on the same figure. And once you complete, before saving or displaying the figure, write hold off to release the figure. And finally, we saved the figure. This for Python and this for MATLAB. Also you find here there is oscillation which is not damped, and it ranges between -1 to 1, and when p equals 1 there is a phase shift like what you see here and here. The same for Python, like what you're seeing here and here. Using any of those, you will find that both of them are undamped oscillations. The second category is called damped oscillations, and it's opposite to undamped because in this case, the oscillation will be damped after a certain time, and rewarded systems often experience energy dissipation due to friction, resistance, or other forces, and this leads to decreasing the amplitude over time. So if this is the general solution, then just replace m by 1, c by the value 2 omega, and k by the same value omega naught squared. And also in this case, there is no external force, so f of t equals 0. Again, x is a displacement or deviation from equilibrium, omega is a damping coefficient, and there is an equation here that calculates the omega using c and m. So if you have c and m from the original equation, you can substitute and get omega. Omega naught is the natural angular frequency of oscillation and also can be calculated using this formula. And we will need zeta, which is the damping ratio, and it determines the type of damping, and zeta is calculated using gamma over omega naught. And once you reach this formula, then you can say you are in damping phase. But what type of damping? This is determined, as we noted, by using the zeta factor. So we check the equation, determine what type of the oscillation or the type of the oscillatory behavior. If it's damped oscillation, then calculate zeta, which is the damping ratio, and based on it, determine what type of the damping. Once you get zeta, you can determine if this equation or the system is underdamped if zeta below 1, critically damped if zeta equals 1, overdamped if zeta is above 1 or greater than 1. For the undamped oscillations, a system oscillates with a gradually decreasing amplitude where a new factor called omega d is the damped angular frequency, and it equals to the square root of omega naught square minus gamma square. And by calculating this factor, we can get the general solution to look like that: the exponential of negative gamma t multiplied by c1 cosine omega dt plus c2 sine omega dt. You can replace c1 and c2 by the constants a and p, whether this or that. Both of them are constants. And if you notice, this equation looks like the equation of the undamped oscillation, but we added here the exponential, and instead of omega naught, we are using here omega d. For the critically damped oscillations, where zeta equals 1, the system returns to equilibrium as quickly as possible without oscillating. And here, the general solution will be the exponential multiplied by c1 plus c2 multiplied by t. For the overdamped oscillation, where zeta above or greater than 1, the system returns to the equilibrium point slowly without oscillation. So in critically damped and overdamped, there are no oscillations, and the system returns to the equilibrium. The difference is that in critically damped is to tell the system to return as quickly as possible, but in overdamped, it returns slowly. The general solution in this case for the overdamped oscillation will be c1 multiplied by the exponential plus c2 multiplied by the exponential. The first exponential is exponential of r1 multiplied by t, where the second exponential is the exponential of r2 multiplied by t. r1 and r2 are the roots of the system, and these roots are real, distinct, and negative roots, and can be calculated using these two formulas. r1 is equal to negative gamma plus the square root of gamma square minus omega naught square. The same for the second root, but instead of plus, it will be minus here. There is a typo. This will be r2. There are many applications for each of them. For example, the undamped oscillations. It's like the heartbeat response after physical exercise, where the heart rate oscillates before stabilizing. And for the critically damped oscillations, it's like muscle contraction returning to rest without overshooting, like when you are lifting or lowering an object smoothly. And the overdamped oscillations is like joint movement with high fluid viscosity or excessive tissue stiffness, causing a slow return to the resetting state. So let's start one by one and describe the corresponding code for each of them. So let's begin by the damped oscillations, where zeta is lower than 1. Open the code. Lecture 4, lab exercise 2 damped. We will begin by importing the necessary libraries. Again, we are importing NumPy and Matplotlib. Let's skip these comments for a while and let's go to this block. If zeta is lower than 1, we are printing some statements to notify the user that this equation is undamped oscillation, and this is the general solution, and this is the equation for the omega d, and omega d is a damped natural frequency, and A and P are constants determined by the initial conditions. And then we calculated omega d using the equation square root omega naught squared minus gamma squared, and then used omega d to substitute in the general solution to find the corresponding x. Omega naught and gamma are defined at the beginning of the script, and zeta, as mentioned, equals to gamma over omega naught. So if we commented these two lines and used these two lines, so in this case omega naught is 2 pi and gamma is 0.1. In this case we are in the underdamped phase, or this example refers to underdamped oscillation. So in this case this block or this section will be executed. Let's skip both of them until we describe the underdamped oscillation. If the underdamped oscillation block is executed, then we calculated the corresponding x, and now we are plotting t versus x, the displacement and time, and saving the figure, and finally plotting it and showing the plot. This is the corresponding execution when zeta is below 1, and this is the log that will be printed on the command window, and these are the calculated parameters. These are the defined ones. This is zeta. These are the values for A and B, the constants. And if you look at the figure, you will find that there is oscillation, but this oscillation decreases over time until at a certain point it will reach to a very smooth line, something that looks like that, or even looks like that. So for the overdamped, you will find zeta is below 1 and the oscillation is damped after certain time, and this is the corresponding MATLAB code. Let's go to describe it. Open the corresponding MATLAB code. You will find the same comments with the same values, the same calculation for zeta, gamma over omega naught, the same values for A and P. We defined the time from 0 to 25 with 1000 points. We printed the parameters and defined the blocks. There is the first block where zeta is below 1. We printed the same statements, calculated omega d, and based on that calculation we calculated x using that omega d and gamma, and at the end we plotted and saved the figure. If you executed the code, you will find the same values and parameters as you look here, and there is the corresponding plot. It will also decrease and reach to equilibrium or to be stable over time, and this is another problem with the underdamped. The first one got a zeta of 0.01. The second problem got a zeta of 0.19. And if you look here, whether you're using Python code or MATLAB code, you will find the same figures. But if you look at any of these two figures, you will find that the oscillation is damped nearly 5 seconds and then continued to be stable over time. So it's not necessary that the oscillation continues for a long time. It depends on the zeta value and the parameters. And these values, as we mentioned, is calculated using omega naught and gamma. And omega naught and gamma are calculated based on the constants C and M and K. And by changing the values of these constants in the original model, we can make it faster or slower to reach equilibrium or reduce the overshooting All of that are listed under the characteristic of the system. One of these characteristics is called overshooting, and overshooting means that the system gets a higher value than the intended value and then returns back. So if the intended value or the amplitude should be 1, so you'll find, if you zoomed in, you will find at 1 that the system increased slightly and then return it back. This value is called overshooting. Also, if you return it back to the previous example for the overdamped also, you will find there is another value for the overshooting. So the aim here is to understand how the system or the model behaves, because you might get a system that looks like that, and after solving the equation and plotting it, you will find a figure similar to this one. So you may return back to the original system and modify it so that you can make it settle faster and reach to equilibrium faster. Rather than 5 seconds, it may settle at 1 second or below. Let's move to the critically damped oscillation example. And here we defined omega naught to be 0.25 pi and gamma to be 2 pi. And in this case, the damping ratio or zeta will equal to 1. Let's return to our script. Let's comment this and uncomment this. Omega and gamma have the same values, so there is a typo here. There should be 0.25. And once you calculate zeta, which will be in this case 1, then this section will be executed. Again, we are printing set of statements, and then we define the general solution and substitute it with gamma t, p, and a, and got the corresponding x. And also, this will be plotted with the new x value, and this should be the corresponding figure in Python. As you see, there are no oscillations. It starts from 1 and decreases as quick as possible until it settles to 0. The same for MATLAB. Here, the block should be executed. We are printing set of statements and substituting in the equation and plotting the figure. And this should be the corresponding MATLAB figure. Again, there's a typo. It should be 0.25. And finally, for the overdamped oscillation, it should look like the critically damped. There are no oscillations and it decreases, but it decreases slowly. So if you return to that figure, it reaches between 7.5 and 10 seconds to equilibrium. And here it reaches to the equilibrium around 15 seconds. So the critically damped is faster than the overdamped, as we defined in the definition from a while. And for the code, else here means it's not underdamped nor critically damped, and in this case it will be overdamped. We printed a set of statements to define the general solution, the values for R1 and R2, and what A and P are. We calculated R1 and R2, the roots of the equation, and then substituted to get the corresponding x. Using this x, we can plot it. And for Python is the same. Else, print statements, find R1 and R2, calculate the corresponding x, and then plot it. So this script, whether you're using Python or MATLAB, do the same function. You are defining parameters, calculating zeta. Based on the zeta, the corresponding section will be executed, whether it's underdamped, critically damped, or overdamped. Once you get it, you will get an x, and you have the time. You can plot both of them, the time versus the displacement, and you can later save the figure and display it. This is the Python figure, and there's the corresponding MATLAB figure. Now, we mentioned damped oscillations and undamped oscillations. For the damped oscillations, based on the zeta value, we can say it's overdamped, underdamped, or critically damped. And for each of them, we got the corresponding general solution. There is another type called forced oscillations, and it's driven oscillatory systems. And this happens when an external force drives the system. And in this case, oscillations may persist indefinitely. And here, instead of setting this by 0, we will get f of t with the same equation. And f of t here represents the external driving force, such as the rhythmic nervous stimulation. And in some cases, if the frequency of f of t matches the frequency of the natural frequency omega naught, then the system experiences resonance, and resonance here means large amplitude oscillations may occur, and resonance is important in understanding how biological systems respond to the rhythmic stimuli. And there are many other applications in bioengineering and biology that uses this model, such as heart rate response to exercise using external rhythmic stimuli like running, and neural oscillations where brainwaves are driven by external sensory input, and also muscle twitching under electrical stimulation, where the rhythmic electrical pulses cause repeated muscle contractions, and there are many more examples. The last category is called self-sustained oscillations or nonlinear oscillators, and here some biological systems generate their own oscillations without external forcing, and these systems maintain oscillation without continuous external input. The amplitude and the frequency stabilize over time due to nonlinear feedback. There are many nonlinear differential equations. A common model is called van der Pol oscillator, and we have a second derivative plus mu multiplied by 1 minus mu squared multiplied by the first derivative plus x equals 0. So there is no external force, but this model has an internal and nonlinear feedback, and this will generate nonlinear oscillators. Here, this value is greater than 0, and it controls the strength of the nonlinearity. So now we have 4 categories: undamped, damped, and it's categorized into 3 subcategories. The third is forced oscillation, and the last is self-sustained oscillations. This is a tabular summary for the oscillatory behavior. You will find the model type in the first column, the differential equation form in the second column, and the behavior of each of them in the third column, and finally an example in biology or bioengineering. For example, between critically damped and overdamped, it's fast to return to equilibrium, but it's here slow. Both of them has no oscillations. For the underdamped, we have decaying oscillations, but for the undamped, constant amplitude oscillations. For the forced oscillations, we have sustained oscillations, and self-sustained, which is the last one, follows the van der Pol equation, and here we have a stable limit cycle and internal nonlinear feedback that causes the system to oscillate. Now let's move to a case study to collect all of that together. So the problem here is modeling heart rate dynamics using second-order differential equations, where heart rate dynamics can be modeled using second-order differential equation to simulate how the heart responds to external stimuli, such as exercise or stress. Here, the heart behaves like a damped oscillatory system with intrinsic oscillations due to pacemaker cells and damping caused by physiological resistance and regulatory mechanisms. Here, in this case study, we use a simplified version of a mechanical model for a cardiac motion, where the displacement x of t represents the deviation from normal heart rhythm, such as heartbeat force or blood flow variation, and the system follows this equation that we saw in the oscillator behavior, where x of t is the displacement, gamma is the damping coefficient, omega naught is the natural angular frequency, and f of t is the external stimulus. In this model, we will capture the different types of the oscillator behavior depending on the value of gamma relative to omega naught. Using both of them together, we will calculate the zeta, and the zeta will determine also the type, whether it's underdamped, critically damped, or overdamped. For the first 3 of them, we will use the general solution, and the last one, we will use the function solve IVP, initial value problem, to solve the problem numerically. Again, the first 3 has no force, so f of t will equal 0, but the last one will contain a force, f of t doesn't equal 0. Here we are summarizing what's going to be programmed in Python and MATLAB. For the undamped, the factor for the first derivative will be 0, and we will use the corresponding general solution, and the same for the underdamped, critically damped, and overdamped. We will use also the different general solutions, as you see here in the last column and illustrated earlier. And for the last one, we will use f of t equals to f naught multiplied by cosine omega f multiplied by t. And here we will solve this using numerical integration, because analytical particular solutions for many cases can be complex. And in the next lecture, we will understand how to solve a non-homogeneous differential equation, as we are here solving and getting an understanding with how to solve the homogeneous differential equations by proposing a general solution and substituting with the initial values and getting the corresponding particular solution. So for now, we will use Python and MATLAB to find the solution numerically. So we have a model. We need to write a script for that model to fit all of these equations. So simply, if you want to solve something numerically or get the help of the function solve IVP, you need to convert the second order differential equation to first order system. And this can be done simply. First, define new variables and rewrite the equation using these new variables. And this will convert the equation from second order to first order. And instead of getting only one second order, we will get a system of two first order equations. So here we can say we have a displacement x. So let's propose a new variable called v is the velocity, which is the rate of a change of displacement, and v equals dx by dt. So if we find the derivative of the velocity, we will get dv by dt equals to the second derivative of the displacement. Now, by substituting using dv by dt instead of the second derivative, we can get rid of the second derivatives or the second order differential equation. Let's rewrite it. Replace this by dv by dt, like here. Replace this by v, and we have x. Keep everything as it is. Now, we need to get the two first order differential equations. The first is dx by dt. The second is dv by dt, because we have here two variables, x and v. So dx by dt is equals to v, is the velocity, and dv by dt can be found from here by simply moving other factors to the right hand side. So it will be negative 2 gamma v and the negative omega naught squared x, and the last term plus f naught cosine omega f multiplied by t. Using these two first order differential equations, we can write our script. So let's go to script named lecture 4, lab exercise 3, heart. We defined the necessary libraries, numpy, matplotlib, and imported the function solve initial value problem. We defined a function that can fit to the different problems, whether it's undamped, damped, or forced oscillations. Here we accepted time and y in this case, because we are dealing with a second order differential equation, will contain two state variables, x and v. We accepted also omega naught, gamma, f naught, and omega f, and these are for the right hand side for the equation, and initially they are set to 0. First, we unpacked x and v from y and define the different derivatives. Dx by dt equals v, and dv by dt equals to negative 2 gamma v minus omega naught squared multiplied by x plus f naught cosine omega f multiplied by t. And here we are returning dx dt and dv dt. So this equation, if got f naught 0 and omega f 0, can be used with the undamped and damped oscillations. If f naught and omega f with values, then we switched the gears to forced oscillations. In our script, we defined omega naught for all of the cases with 2 pi, and the initial displacement x was 1 and v was 0. We defined the time from 0 to 20 seconds with 1000 points, and we defined a list of colors, so later we can plot each case with a unique color. We have 5 cases, so we set here 5 colors. Then we defined a dictionary with the 5 cases: undamped, underdamped, critically damped, overdamped, and forced oscillations. For each of them, we define the corresponding parameters for gamma, f naught, and omega f. As you notice, for the first 4 cases, f naught and omega f are zeros, while the last one got values. Then we started to solve analytically the problem for the first 4 cases. We started by defining the undamped equation, and it's worth noting here we defined values for A and B, but actually the values for A and B can be retrieved using the initial conditions and substituting in each general solution and getting the output and the values for A and B. But for now, we set these values for A and B for each case just for illustration. We got the undamped, then we calculated the underdamped by defining there is omega d and calculating it. Then we calculated the critically damped, and all of these equations are similar to what we calculated in exercise 2 here. And last, we calculated the overdamped. So now we have 4 equations or 4 variables: undamped, underdamped, critically damped, and overdamped. Then we calculated, to validate our results, the solutions numerically for all of them using the solve IVB. So if the curve or the plot of the analytical solution and the numerical solution are close enough, so we can say we are plotting them correctly and calculating them correctly. So here we created an empty dictionary to be filled later with the different solutions. Then we looped on the dictionary, which we defined earlier here. Then we used solve initial value problem. We defined a lambda function by calling the hard oscillations, passing t and y, omega naught, the corresponding gamma value, and the corresponding f naught and omega f values. Then it requires a time span and the initial conditions, and also the time points. So we are passing t span, y naught, and t eval, which are calculated at the beginning of the code here. After getting the solution, we are assigning it using the corresponding key to the solutions dictionary. Now we have 4 variables and dictionary. We need to plot each of them separately so that we can put each of them side by side and compare if they are close enough or not. First, we created the first subplot to include the 4 plots for undamped, underdamped, critically damped, and overdamped with the corresponding colors: first color, second color, third color, and fourth color. Then we set title, labels, legend, and created a grid. Then we created the second subplot, and here we looped on the solutions dictionary and plotted each of them, and also set different configurations such as labels and title. And finally, we saved the figure and displayed it in front of you. If you executed the code, you will find the first subplot on the left for the analytical solution and the second subplot for the numerical solutions. And here you'll find that the undamped for both of them are close enough or similar. The critically damped here and here, the overdamped here and here, and the underdamped here and here. And also for the forced oscillation, you will find it in purple. So by looking at both of them, these 2 figures or these 2 subplots, we can determine that the analytical and numerical solutions are close or match each other, and we are correct. If we switch it to MATLAB, we did the same thing. We defined the parameters, the colors, and defined a dictionary to contain the different configurations. And here, for each configuration, it's called struct, and it contains gamma with 0 here, f is 0, omega f was 0, and the same for others. Then we started to apply the analytical solutions here for the undamped, here for omega d and underdamped, here for the critically damped, and here for the overdamped after calculating R1 and R2. Then we switch it to calculate the numerical solutions, and here we use the function ODE45 by calling the function hard oscillations and passing the same parameters. And you may wonder, where is this function? As in Python, we defined it at the beginning, but in MATLAB, if you want to write a script and define a function, write it at the end of the script. So if you scroll down at the end of the script, you will find the function. It gets the same parameters, and here we got x and v. Unpacking them, we got dx by dt and dv by dt, and we returned both of them. So when you call it and define the values for the parameters, you will get two numerical and x numerical. So we are creating a t numerical and x numerical struct and storing it in the solutions, which is created here as empty cells. And finally, we plotted both of them. This is the first subplot, x damped, underdamped, critically damped, and overdamped. And don't forget hold on and hold off after you complete. And for the second subplot, we are looping on the solutions and plotting each of them. And also don't forget hold on and hold off. And finally, we are saving the figure and displaying it in front of you. And there is a corresponding figure, the two subplots, analytical solution and numerical solution, undamped, which is here and here, the blue one for the underdamped here and here, the critically damped and overdamped here, critically damped and overdamped here, and here is the forced oscillation. So in this lecture, we have discussed the second order differential equation and mentioned that there are homogeneous differential equation where the force is zero, and non-homogeneous differential equation where the force has a value, whether it's constant or an equation of t or an equation of a variable. Then we specify the characteristic equation and the discriminant that determines the general solutions based on the discriminant value, and we ensure that the characteristic equation should get a homogeneous equation and the coefficients for a, b, and c should be constants. Then we switch the gears to oscillatory systems, and in oscillatory systems we said we can get undamped oscillations, damped oscillations, and forced oscillations, and the last category is the self-sustained. In the damped oscillations we subcategorized into underdamped, overdamped, and critically damped. And finally, by the end of the lecture, we presented a case study which is modeling heart rate, and we defined different cases and conditions where sometimes we can get undamped and sometimes can we get critically damped, and all of that depends on the value of zeta or the value of omega naught and gamma. We are now able to handle a second order differential equation whether analytically or numerically, and most of the homogeneous differential equation from the second order, you only write the general solutions and substitute with the initial conditions if you have to get the values of the constants, and using that you can plot and visualize the figure of the system. And if you don't have constants or initial value problems, you can assume these values as we did in the example here.